Alright, welcome back. This is physics tutoring. Today I'm going to start talking about motion in one dimension. And to do so, we're going to have to define some properties. The first property I'm sure we're all quite aware of is space. Space in general. We talked about units last time, and we're going to be measuring space in meters. And so we call that displacement. So, for example, if I walk from here 2 steps here, I've displaced myself a certain unit. If I walk 2 steps really quick, I've displaced the same amount. So displacement only has to do with where you started and where you finished. And this is probably a good time to bring up the delta notation. So we're going to use the x-axis for our first dimension. So if I were to write delta x, what does this mean? Well, what this means is that I'm including delta x is the change in x. That's what big delta stands for, and in calculus we use d for instantaneous rate of change, and that stands for lowercase delta. So, but uppercase delta is going to be more used in the physics 111 course, and lowercase delta is going to show up in the physics 211, but we're just going to kind of stick with the basics at this point. So this includes where I started and where I ended. So I started here, I took 2 steps here, and so I finished somewhere, and so I've started somewhere and I finished somewhere. And we call those points the initial state and the final state, right? So I started here, that's my initial state, I went there, that's my final state. Now what if I wanted to find the displacement or the distance that I traveled, right? Remember, displacement's a vector, it includes the information of where I'm going, whereas distance just includes how far I went. So if I wanted to figure out the displacement I went, I would take the final state, right? I would take the final state and I would subtract the initial state. And that would give me the difference between the two, right? We call that a difference, subtraction. And so when you see delta x, I want you to think x final minus x initial. And I'm writing this in vector form. In one dimension, you don't have to worry so much about vectors because you remember, in one dimension, all vectors are on the same line. And so you don't really need to worry about the x hat component, the y hat component, the z hat component, because everything in the x dimension is all in the x hat direction. And so, but this is just to get us used to when we, for example, go into motion in 2 dimensions and maybe even 3 dimensions. And so this is our first quantity, x, it's displacement. Now we want another quantity, because remember, it doesn't matter how fast I go from my x initial to my x final. No matter how fast or slow I go between these 2 points, the displacement will remain the same. Well, we know that getting places quicker or slower is an important thing in physics, and so we wanted to come up with a few quantities that would describe how fast we were changing our position with respect to time. And so we came up with something, well, not we, somebody much smarter than me came up with the idea of velocity. And velocity is going to be defined, the average velocity is going to be defined as the change in position with respect to time. And so up here, of course, displacement units are in meters. And you'll notice, using a little bit of dimensional analysis, we have meters over seconds, right? So velocity is meters per second, so units, meters per second. And that makes sense. So now we're not only measuring how far I went, we're measuring, like how many meters I'm covering in a given second. Am I covering a few meters in a given second, fractions of meters in a given second? And so velocity, for example, let's go ahead and draw a two-axis plot here. The y-axis will be the x dimension, and the the x-axis will be the time direction. So as time goes on, as time goes forward, how much are we moving? And so if you have a constant velocity, like for example, you're going 4 meters per second, well then what you're going to see is you're going to see, and let's say this is your initial point, and you're moving up here, and you're going to your final point, and you're going at 4 meters per second. Well, that is representative of a slope, right? So 4 meters, that's in the x direction, meters are in the x direction. So we've got 4 meters per 1 second. And so what that means is we have a right triangle here. Let's see here, I'll use blue. So here we've got 4 meters per 1 second. And so if we have a 1 second run to a 4 meter rise, well, if we remember y equals mx plus b, this is representative of the slope of the displacement. And so what we end up with up here is a slope of 4 meters per second. And so as you increase velocity, it will take you less time to travel the same distance. Let's say these are the same distance. But if I have a higher slope, like 7 meters per second, it will take me less time to travel a larger amount of distance in the x direction. And so what we're looking at here is, up here on the x-axis is our x final, down here is our x initial, and here's our x final for the first example, 4 meters per second. So you see, if you increase your velocity, you get places quicker. But this alone just isn't quite enough to describe everything that we want to. For example, when a runner starts a race, or when a car gets into motion from a stoplight or a traffic signal, they never go from 0 meters per second to 60 meters per second, or for us, miles per hour is a little more familiar. There's always some transition time that it takes to get up to speed. And as you're changing your velocity, so if we start at 0 miles per hour and we get up to 60 miles per hour, there's a change in velocity there, right? We're no longer dealing with a constant velocity, like 4 meters per second or 7 meters per second. Now we're actually having to change our velocity over time. So we're no longer dealing with constant velocity, we're now changing velocity with respect to time. And so we go ahead and define another concept of acceleration. And we define acceleration as the change in velocity with respect to time. And of course, as you can see here, velocity is using a little dimensional analysis again, using our unit knowledge. Velocity is in meters per second, and time is in seconds. So units is going to be meters per second And that kind of makes sense, because when we started at displacement, we had meters. Then we wanted to see how many meters are we getting per second. Well, now we're interested in how many meters per second we're getting per second, right? So that's how much our velocity is changing per second, delta V over delta T. And typically, we'll write this as meters per second squared. But I kind of prefer, for a logical understanding of acceleration, I prefer to think about it as meters per second. But of course, everybody's going to call it meters per second squared. This confused me for quite a long time. Once I thought of it this way, I kind of started to understand what it was. And of course, the multiplication here is, you can invert and multiply, because division is the inverse operation of multiplication. So when we invert and multiply, we get meters times 1 equals meters, and now seconds is on the bottom. Second times seconds is seconds squared. So yeah, now we've got meters per second meters per second squared. And so now we're looking at acceleration. Well, acceleration isn't actually the end of the line. It's kind of where it ends for this class, because there are higher orders, right? You can keep this going. Like, what do we call it? What do we call a change in acceleration with respect to time? Well, we call it a jerk. And what do we call a change in a jerk with respect to time? We call it a joust, I think. But most everything that we deal with in this class is, well, actually everything we deal with in this class is going to be within these first three orders of motion. And the main reason why is because of gravity, right? So gravity has a constant acceleration. And so since it has a constant acceleration, we don't need to worry about jerk. We can go ahead and just ignore that and deal with, constant acceleration problems. And so this is just an introduction to some of the concepts that we're going to be describing in greater detail. Next video, we're going to go over the equations that govern motion in any number of dimensions, but we're going to approach it from a motion in one dimension perspective. So I hope this was helpful, and I'll see you next video.